So what we're going to do now is derive an equation called the wave equation. This is a second order differential equation, which is d squared y dx squared is equal to 1 on v squared d squared y dt squared. This can be applied to all waves. Applying it is a bit beyond the scope of this course, but it's important that you see this derivation. So we'll cover the derivation now. So we're going to imagine a wave travelling along a piece of string like this, and so these two forces here are both tensions pulling on the string, and at this moment the string is being accelerated upwards. Okay, so looking at this, we can say that the magnitude of F2 is equal to the magnitude of F1 because these are both equal to the tension in the string T. And now to derive this wave equation, we're going to start with Newton's second law. So we're going to start in the y direction. We know that F2y minus F1y is equal to ma. In this case it's dm because it's a small mass on this increment times ay. So that's just Newton's second law. And now we know that because it's a string, dm is equal to mu dx, and we know that ay, that's the acceleration in the y direction, so that's d squared y dt squared. So now what we're going to do is we're going to look at the slope of these lines here. So the slope of the string is really the same as the kind of slope of the force, if you like. So let's say S2, that is equal to F2y over F2x. So we can think of this as a rise over run or a slope. You'll see why we do this in a little bit. And then S1 again is F1y over F1x. And so now we can call the difference between these two slopes, S2 minus S1, is equal to ds. This ds is a very small number because this wave is travelling along the string, so we've got almost the same slope there as there. Okay, so now what we know is that F2, this second force, is been broken into two components, y and x, and so Pythagoras' theorem tells us that this is F2x squared plus F2y squared. But also because this is a pulse travelling along a string, we know that the displacement of the pulse can't be large compared to the string. So we know that F2y is a lot less than F2x. So this is approximately equal to F2x, which we can also call equal to, looking at this equation up here, this is equal to F2y on S2. Now we can do the same thing for F1. F1 is approximately equal to F1x, which is equal to F1y on S1. So now using that F2 and F1 have the same magnitude, let's substitute into this top line up here. So F2y is equal to F2 times S2. F1y is equal to S1 times F1, so S1, F1, but what we're going to do is replace this F1, because it's got the same magnitude as F2, with an F2. So there we go, there's our F2. And this thing is equal to this thing, which is the mu dx, times d squared y dt squared. Okay, now S, we said S was the gradient, so S is equal to dy dx. So what we've got here is F2 ds. So let's put this as ds, which is equal to mu on F2. Now we're going to move this dx over to the other side, so there's the dx times d squared y dt squared, which tells us that S, this is d of dy dx, so that'll be d squared y dx squared is equal to mu over F2, which is the same as the tension, so let's put the tension there, d squared y dt squared. Now previously we've shown that the velocity is equal to square root of tension over mu, and so we've got v squared is equal to t on mu, so we can replace this mu on t with 1 on v squared. So we've got d squared y dx squared is equal to 1 on v squared dy d squared y dt squared. And so that is how we derive the wave equation.